Often when we are looking at a random variable, it's beneficial not to look at the entire probability mass function, this complicated function that tells us all the information about a random variable. Instead, we might be interested in a summary, and a summary that you've seen in many areas of your quantitative life is the idea of an average. So we can define the idea of an average for random variables as well, and our terminology here is called expectation. So we talk about the expectation of a random variable. So definition, let x be a random variable with some set of possible values that here I've notated as fancy x. Then the expectation or expected value of x, these mean the same thing, is defined as follows. We use a fancy e and then we put x in brackets, and that's our notation for the expectation of random variable x. And the way we define it is we take every possible value of x, we multiply by the probability mass function evaluated at that value, and then we sum up all of the results. So let's look at a few examples. So here's one example. Suppose I flip a coin with probability of heads equal to P. So this coin doesn't have to be fair. Maybe it's a coin that has probability of heads equal to 70% or something like that. Let's let x be the number of heads, and I'm only going to flip one coin, so the possible values for x are 1 or 0. So what I want to know is what's the value of the expected value of x? Well, let's parse this out. By definition, it's the sum across all possible values of x, and here the possible values are just 0 and 1. So I look at all the possible values, 0 and 1, and then I'm going to multiply little x times the probability mass function evaluated at little x. So we have two terms, one term corresponding to x equals 0 and one term corresponding to x equals 1. For the x equals 0 term, I'm going to have 0 times the probability that the number of heads is equal to 0. Well, that's the same as the coin I flipped coming up tails. So the probability of that is 1 minus p. If the probability of heads was p, the probability of tails has to be 1 minus p. On the other hand, I have another term. What if x is equal to 1? Well, in this case, I'm going to multiply 1 times the probability mass function evaluated at 1. That's the probability of getting 1 heads in this experiment. And that's by definition equal to p. And so the result at the end of the day is p itself. The expected value of this random variable is equal to p. Now, something you might notice here is that p is not an integer. It's not 0 or 1. It's not a valid number of heads to get. And so this is an important thing to notice. The expected value of x doesn't have to be a possible value of x. The expected value here might be, if p is 70%, the expected value for the number of heads could be 70%, even though that's not a possible number of heads for me to get. Heads has to be either 0 or 1, but the expected value could be fractional. So this is a common pattern and sort of funny little trope is that back in some era in history, the nuclear American family had 2.3 children on average. So this is an expected value. It was not the case that any given family actually had that number of children. So let's do another example. Suppose now that we flip 3 independent fair coins, so 50% probability of heads, and let x again be the number of heads. Then let's see if we can figure out the expectation of this random variable. So to do this, we are going to consider an outcome. We're going to consider the probability associated with that outcome, and then we are going to consider the value of the random variable associated with that outcome. So for our outcomes, we can get heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, or tails, tails, tails. All of these have the same probability of 1/8 because the coin is fair and I'm flipping it independently in each flip. And then the value of x here, the number of heads, I see 3 here, 2, 2, 1, 2, 1, 1, 0 for my measurements. Okay, so now we can construct the probability mass function. So the probability mass function evaluated at 3, that's the probability of getting 3 heads, that's 1/8. The probability of getting 2 heads here, well, I see 3 outcomes where that occurs, each of which has probability 1/8. The probability of getting 1 head, similarly, I see 3 outcomes where that occurs with probability 1/8. And then finally, I have the probability of seeing 0 heads, which is 1/8. So now I can compute the expected value. So if I want to know the expected number of heads here, I can sum across all possible values of x of little x times my probability mass function. So the x equals 0 term is 0 times 1/8, plus I have an x equals 1 term, that's 1 times 3/8. I have an x equals 2 term, that's 2 times 3/8. And I have an x equals 3 term, which is 3 times 1/8. So if we add these up all together, we'll get 12/8, which is equal to 3/2 as the expectation of this random variable. You'll notice 2 things. One is that this, again, is not a valid number of heads to get. My expectation doesn't have to be an actual realizable value. And you'll notice something else, which is that this looks suspiciously like 3 times the expected number of heads for 1 coin. So you might say, hey, Phil, why didn't we just compute the expected number of heads in 1 coin, that would be 1/2, and multiply it by 3? And the answer is that's a valid thing to do, and when we learn about indicator variables, we will solve this problem that way as well. So when we have multiple random variables flying around, we can also combine them in ways that involve computing expectations. So there's 2 ways that I want to focus on here. First of all, and maybe most importantly, is what we call linearity of expectation. So theorem, let A and B be some constants. So these are not random numbers, they're not random variables, they're constants. But let x and y be random variables that are defined on the same sample space. Then what we are going to do is we're going to say, hey, I want to know the expectation of some constant multiplying x plus some other constant multiplying y. And as we can show with a direct calculation that we're not going to do together here, if I want to compute this expectation, I can compute it more simply by saying, hey, this is equal to the constant multiplying x times the expectation of x plus the constant multiplying y times the expectation of y. I don't need to do anything with all of these together. I just need to know the expectations of x and y separately in order to compute this more complicated expectation here. So this is called linearity of expectation. That lets me decompose sums of expectations into simpler ones. And something really important about this works for any random variables defined on the same sample space. It doesn't matter whether they're independent or not specifically. This works even if those random variables are not independent. We can generalize this with induction. So if I have some big set of real numbers, n of them, as well as some set n of random variables defined on the same sample space, then I can decompose a big complicated sum where I multiply each of them by my scalar constant and then add all those up. I can decompose this into a simpler sum where I pass the expectation inside the sum. It becomes associated with each random variable independently and separately. And then I just add them all up, incorporating these constants here. So again, if I know the expectations of each of my individual random variables, that's enough for me to figure out everything I could ever want to know about the expectation of a sum of random variables. And again, I don't need independence for this. Something I do need independence for, however, is multiplication. So a theorem, if x and y are independent, then it's the case that the expectation of x and y is equal to the expectation of x times the expectation of y. If x and y are independent, it's very, very important to note that this does not work without independence. If your random variables are not independent, this is not in general going to be true. So you can only factor expectations into simpler expectations when you have independent random variables. It's also the case that this can be true sometimes in certain specific cases, even when x and y are not independent, but you never know when those cases are. They're kind of funny little counterexamples rather than anything you can depend on. So if you want to be able to factor an expectation of a product of random variables, the first thing you need to do is check if they're independent before moving on. Let's go ahead and do some examples of computing expectations with multiple random variables. So we have our two main theorems from the last discussion. So first of all, we have linearity of expectation, which says that if we have sums of random variables, we can distribute the expectations over the sums, and we can factor out constants as well. And then we also know that if two random variables are independent, then their expectation of their product factors. So let's see if we can look at some examples here. What I'm going to do is I'm going to flip two independent coins, not fair. They have a probability of heads equal to p, so they might not be fair, they might be crooked, maybe the probability of heads is equal to 3/4 or something like that. But I am going to flip independently. So let's suppose that we measure x, the number of heads, and y, the number of tails. What I'd like to know is what's the expectation of x plus y, and what's the expectation of x times y. So let's see if we can work these out. In order to compute the expectation of x plus y, this part's actually not too complicated. So in order to compute the expectation of x plus y, well, we know that the expectation of x plus y has to be equal to the expectation of x plus the expectation of y. Okay, so we need to figure out the expectation of x, and we need to figure out the expectation of y. So to do this, what we are going to do is we can actually enumerate, again, our sample space here. So here's heads, 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 tails, tails, heads, and tails, tails. And what are the probabilities of each of these outcomes? So here's the probability of each outcome here. Well, two heads means that something with probability p had to happen independently twice, so that's p squared. One heads happened with probability p, and then one tails happened with probability 1 minus p, similarly here. And then the last one, 1 minus p squared. Okay, so then x and y in these cases had values 2, 1, 1, and 0 for the number of heads, and then 0, 1, 1, and 2 for the number of tails. And now we could go on to just actually look at x plus y directly, but instead I want to look at the expectations of x and y. So here, let's calculate the expected value of x. The expected value of x is equal to 2 times p squared, so that's the probability of getting 2 heads times 2 for the number of heads, 2 times p squared plus p times 1 minus p plus another p times 1 minus p. So that's 1 head multiplied by the probability of getting exactly 1 heads. There's also a term that involves multiplying by 0 that we're going to skip. So if I simplify this out, actually, the result that I'm going to get is 2 times p, which you can check with some algebra. And then a similar calculation shows me that the expected value of y is equal to 2 times 1 minus p. So this means that I have all the information I need to calculate the expected value of x plus y. I need to separate them out and then add. And so I'm going to get 2p plus 2 times 1 minus p, which is equal to 2. And the reason this answer makes sense is that every coin flip has to be either a heads or a tails. So if I add them all up, then really I'm just asking what's the expected number of coins that I'm flipping, and that's always 2. And so I know that at the end of the day, I'm going to get 2 here if I add up all my heads and my tails in this experiment. Okay, so a little bit more complicated, though, to look at e of x times y, the product. So to do that, what we're going to do is we are going to measure this product in the sample space as well. So here, if I multiply x times y, I get 0, 1, 1, and 0 here. So that means, by definition, the expected value of x times y is equal to, okay, let's check it out here. We are going to ignore all the terms that involve multiplying by 0, so we're just going to focus on these guys, which means that we have 2 copies of p times 1 minus p. So that's what I got by adding up these two outcomes. So notice that this is different from what I would have gotten by computing the expectations individually and then adding. So each of these individually here, so 2 times p, 2 times 1 minus p, if I multiply those together, I would get 4 times p times 1 minus p, which is not the value of the expectation of the product. So in this experiment, we saw both an application of linearity of expectation, allowing us to compute the expectation of a sum by decomposing it into a sum of expectations, as well as an example where, because our random variables were not independent, it wasn't possible for us to decompose the expectation of the product into a product of expectations. We had to compute it directly. Instead, if we'd tried to use the product formula, we would have gotten the wrong answer because we didn't check for independence, and indeed, in this case, independence was not satisfied. So be careful out there.